More gold has come out of one stretch of ancient rock in South Africa than from any other place on Earth by a ridiculous margin. Since mining began in 1886, the Witwatersrand has yielded around 48,000 tonnes of gold, roughly 40% of all the gold ever mined in human history. At today's prices, that pile of metal would be worth about 10 to 11 trillion Australian dollars, enough to bury every major goldfield in Australia many times over. Yet the strangest thing about this legendary province is that its riches were not locked in glittering quartz veins deep in the crust, but in fossil river gravels that later turned to stone. If you could somehow rewind a planet by nearly 3 billion years, the landscape where Johannesburg now sits would look nothing like the urban sprawl that covers it today. Instead, imagine a world of wide, braided rivers snaking across an ancient continent, the Kaapvaal Craton, one of the oldest pieces of Earth's crust still preserved. These rivers were not flowing over modern forests or grasslands, but across barren, deeply weathered terrain made of ancient granites and volcanic rocks called greenstone belts. Greenstones are old, altered volcanic and sedimentary rocks that often contain traces of gold. Those rivers were nature's concentration machines. As water rushed over the landscape, it picked up sand, pebbles and heavy minerals eroded from the surrounding bedrock. Gold, being dense and chemically stable, tended to settle out in high-energy spots. Bends in channels, gravel bars and erosion surfaces where the current slowed just enough to drop its load. Over time, layer upon layer of this material accumulated in what we now call the Central Rand Group, the main gold-bearing part of the Witwatersrand Basin. The most important gold-hosting layers became what miners later called reefs. But here's the twist: in most goldfields, a reef means a quartz vein, a crack in the rock filled with crystallized silica and gold. In the Witwatersrand, a reef is something completely different. It is mostly conglomerate, which is just a geological word for ancient gravel that has been cemented into rock. Think of it as nature's concrete, made of rounded pebbles glued together by quartz. So from the very beginning, this province was unusual. Instead of narrow, unpredictable veins that twist through the bedrock, the gold was spread across broad, laterally continuous sedimentary layers laid down by rivers. That's why, for over a century, entire mining districts could follow the same horizons for kilometres underground. But those gravels did not stay loose. Over millions of years, they were buried beneath more sediment, squeezed by tectonic forces, and heated deep in the crust. This process is called metamorphism, which simply means changing form. In the Witwatersrand, most rocks reach what geologists call green schist facies, a low to moderate level of metamorphism where temperatures of roughly 300 to 400 degrees Celsius transform minerals but don't melt the rock. Under these conditions, the original river sediments turned into hard quartzite and metaconglomerate. That's why mining the Witwatersrand was still classic hard rock mining. Miners were not panning loose gravels. They were blasting solid rock, hauling it to the surface, and crushing it in mills to liberate tiny grains of gold locked inside. Now here's where things get more interesting and controversial. For decades, geologists have argued about whether the gold was purely a placid deposit, meaning it was concentrated by rivers, or whether it arrived later in hot fluids moving through the rock. The truth, based on modern research, is that both processes likely played a role. On the sedimentary side, there is strong evidence that gold, along with rounded grains of pyrite, iron sulfide, and uraninite, a uranium mineral, was originally transported and concentrated by rivers. The gold closely follows specific layers tied to ancient erosion surfaces called unconformities, essentially buried landscapes that were carved by rivers before being covered by new sediment. These surfaces acted like natural trap floors for heavy minerals. The gold is also strongly associated with particular sedimentary environments, gravelly river channels, shallow shorelines, and high-energy floodplains, which is exactly what you would expect if water sorting was involved. In places, tiny original gold grains are still preserved, further supporting a detrital or sediment-transported origin. But the story doesn't end there. As the basin was buried, it didn't just sit quietly. It was squeezed by tectonic forces, especially along its northern and western margins, where large thrust faults developed. A thrust fault is a type of low-angle fracture where one block of rock is pushed up and over another. These structures created networks of tiny cracks and fractures through which hot, mineral-rich fluids could flow. At the same time, metamorphism released large volumes of fluid from deeper rocks, a process called devolatilization, which just means minerals breaking down and releasing water, carbon dioxide and sulfur gases as they heat up. These fluids likely picked up dissolved gold from surrounding rocks and migrated into the Witwatersrand layers. Once inside the basin, the fluids followed the path of least resistance, along bedding planes, faults, and especially those same unconformity surfaces where gold was already concentrated. And when they encountered layers rich in carbon or iron, chemical reactions caused gold to precipitate out of solution. So what you end up with is a hybrid system. Rivers laid down the initial gold-rich layers, and later, fluids upgraded, redistributed, and concentrated that gold even further. That's why much of the gold today sits in tiny fractures or replacement textures that look hydrothermal, meaning deposited from hot fluids, even though the broader control is still sedimentary. This combination of processes is what makes the Witwatersrand so staggeringly rich. Nature didn't just concentrate gold once, it did it multiple times. First mechanically with rivers, then chemically with metamorphic fluids, and finally structurally through faulting and fracturing. Structure also played a crucial role in shaping where the best grades ended up. Even though the gold is hosted in sedimentary layers, local high grades often line up with zones of intense fracturing related to thrusting. These fracture networks created extra permeability, space for fluids to move, and thus acted like hidden plumbing systems that focus gold into narrow, high-grade streaks within otherwise moderate-grade reefs. This is why modern mining in the Witwatersrand relies heavily on 3D seismic imaging and detailed structural mapping. Even in a conglomerate gold province, you still have to understand where the cracks are. Then, just when you think the story can't get any more dramatic, an asteroid enters the picture. Around 2 billion years ago, a massive meteorite slammed into the region, creating what we now call the Vredefort Dome, the largest and oldest well-preserved impact structure on Earth. The collision generated immense shockwaves, shattered rocks, and produced a dome-shaped uplift that dramatically reshaped the crust. Crucially, this impact did not create the gold. The Witwatersrand deposits were already hundreds of millions of years old by that time, but the asteroid did change things. The impact caused intense fracturing and locally increased metamorphic temperatures, especially near the centre of the dome, where rocks reached much higher grades than elsewhere in the basin. More importantly for the goldfields, it created additional secondary permeability, new fracture pathways that allowed fluids to move through the rocks again. In some areas, this likely triggered further local remobilization of gold, subtly upgrading or redistributing ore within already mineralized reefs. So while the asteroid was not the source of the gold, it helped rearrange the plumbing and added another layer of geological complexity to an already extraordinary system. Another remarkable aspect of the Witwatersrand is how little erosion has removed the gold over time. Many ancient gold systems have been destroyed or deeply weathered away, but large portions of this basin remained relatively intact. That preservation is one reason such an enormous endowment could survive until humans arrived with drills and dynamite. By the late 19th and 20th centuries, miners had turned this buried river system into the most productive gold province in history. Entire cities grew up around shafts that descended kilometres into the earth, following the same thin reef horizons laid down by rivers billions of years earlier. At its peak in 1970, South Africa produced around 1,000 tonnes of gold in a single year, much of it from the Witwatersrand. Over time, production declined as mines went deeper, costs rose, and the richest easily accessible areas were exhausted. But even today, enormous reserves remain. So when you step back and look at the big picture, the Witwatersrand is not just another goldfield, it is a geological miracle built from a rare alignment of conditions: ancient source rocks rich in gold, vast river systems capable of concentrating heavy minerals, deep burial and metamorphism that generated gold-bearing fluids, tectonic forces that created ideal fracture networks, and a late asteroid impact that further reshaped the system without erasing it. Most gold provinces are stories of veins, narrow, unpredictable cracks filled with mineralized fluids. The Witwatersrand is a story of landscapes, rivers, buried worlds, and slow, patient concentration repeated over hundreds of millions of years. And that is why, when people talk about the greatest gold province on Earth, they are not exaggerating. They are talking about a place where the planet itself, over immense spans of time, engineered a treasure beyond anything humans could have imagined. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.